Humans have spent millennia building massive stone structures, but the architectural majesty of Chichen Itza is rooted in fundamental three-dimensional geometry. To actually understand three-dimensional space, we have to look past the physical stone and rigorously define the abstract mathematical objects that occupy it. We begin our axiomatic build with nothing, an empty, boundless three-dimensional void. Inside this void, we introduce two distinct two-dimensional planes. We will call them plane P and plane P', and they exist perfectly parallel to one another. Next, we place two completely congruent flat polygons, in this case triangles, one inside each parallel plane. Because these two flat shapes are identical and lie in strictly parallel planes, they form the bases of our geometric figure. We construct the three-dimensional shape by connecting the exact corresponding corners or vertices of both bases. Mathematically, these newly drawn connecting segments are defined as the lateral edges of the prism. The flat geometric planes that form along these edges, connecting the top and bottom bases, are the lateral faces. Together, they create a complete boundary. This leads to a crucial, often misunderstood definition. Formally, a prism is only this bounded geometric shell. It contains absolutely zero interior points. In everyday language, we usually treat a prism, like a brick, as a solid object that includes its interior volume. But strictly speaking, the mathematical prism is just the exterior frame. Before we can begin measuring the volume of our physical world, we must first rigorously categorize these two-dimensional boundaries that enclose it. A prism is categorized primarily by a single structural property, the exact orientation of its lateral edges. Let's look at two distinct variations of a prism side by side to compare how their edges align with their bases. First, the right prism. Notice that its lateral edges drop down perfectly perpendicular to the edges of its base, meeting exactly at a 90-degree angle. Because of this strict perpendicularity, every lateral face on a right prism is mathematically guaranteed to be a perfect rectangle. On the right, we have an oblique prism. Here, the lateral edges are slanted or oblique relative to the base planes. This slant warps the lateral faces. They are no longer rectangles, but instead form parallelograms. Regardless of how slanted the edges are, the prism maintains an altitude, denoted by h. This is always the strict perpendicular distance between the two base planes, not the length of the slanted edge itself. Because these properties dictate the geometry, standard naming conventions require us to identify both the edge orientation and the shape of the two-dimensional base. Look at the first shape. It has perfectly perpendicular edges and a six-sided base. Therefore, it is a right hexagonal prism. The second shape features slanted edges and a five-sided base, making it an oblique pentagonal prism. And the third shape pairs straight 90-degree edges, with a base made of three equal sides. This is a right equilateral triangular prism. Correctly identifying the subtype of a prism serves as the mandatory diagnostic step required before any mathematical measurement can begin. With the shape classified, we can determine its lateral area. This is the sum total area of all the lateral faces, explicitly excluding the top and bottom bases. To translate this three-dimensional shell into an easily readable two-dimensional plane, we conceptually unfold a right triangular prism to view all its rectangular faces at once. Now we assign algebraic variables. We label the widths of these three separate rectangles as the base sides, A, B, and C. Because it is a right prism, their common height is the altitude, h. Using standard two-dimensional rules, we calculate the area of each individual rectangle. This gives us individual areas of AH, BH, and CH. We combine these individual areas into a single algebraic expression representing the entire lateral area, giving us L equals AH plus BH plus CH. Next, we simplify the equation. By factoring out the common variable, altitude h, the equation transforms into L equals h times the quantity A plus B plus C. Here is the central insight. The expression A plus B plus C is exactly the perimeter, P, of the prism's base. Therefore, the lateral area is simply altitude multiplied by perimeter, L equals HP. While we derived this using the rectangles of a right prism, this fundamental relationship elegantly holds true even for the parallelogram faces of oblique prisms. Once you have the lateral area, you can easily define total area, which accounts for the entire exterior surface of the shape. To find total area, you simply take that lateral area and add the area of the two bases. The formula is T equals L plus 2b. The exact mathematical formula used to find the base area changes entirely depending on the polygon. A square requires a completely different formula than a hexagon. For example, calculating the base area of a triangle might require specialized tools like Heron's formula, utilizing the semi-perimeter of the base. Determining the surface area of complex three-dimensional structures is a direct extension of one-dimensional perimeter and two-dimensional planar rules. Now we shift our conceptual focus. We move past the bounded geometric shell and look instead at the empty space trapped inside it. Volume is the exact numerical measurement of that enclosed three-dimensional space. To measure space, we need a standard, uniform unit. We measure length in single-dimensional units and area in squares. For space, we use a basic cubic unit. Technically, this unit cube is a right square prism where every single edge is completely congruent. The simplest solid to measure is a right rectangular prism, often called a parallelepiped or a box. Let's look at one with specific dimensions: a length of 4, a width of 3, and a height of 2. We calculate the volume by measuring the base layer first. A 4x3 floor perfectly fits 12 individual unit cubes. We complete the proof by stacking the second layer to fulfill the height of 2. The total volume is simply 4 times 3 times 2, equating to exactly 24 cubic units. Volume calculations represent a literal physical count of standardized cubic units, tightly packed within a strictly bounded limit. In exploring the geometry of prisms, we've walked a clear mathematical path. We escalated from simple one-dimensional lines to two-dimensional parallel planes, all the way to fully realized three-dimensional solids. Every step up in complexity directly inherits the rules of the dimension below it. This gives us our three master formulas. Lateral area equals altitude times perimeter, total area equals lateral area plus two bases, and volume equals length times width times height. None of these formulas operate as disconnected rules. They all trace their lineage straight back to the properties of their initial base shape. Translating a flat polygon across an altitude defines the entire structural anatomy of the resulting prism, because measuring the physical complexities of our three-dimensional universe relies entirely on our ability to logically master flat geometry.